So this is section 6.3, which is all about exponential functions. Exponential functions are any function that has a variable in the exponent. And we look at them, they're usually written like this: f of x equals b raised to the x power, or y equals b raised to the x power. Now this b here is not a variable. This b is actually a number. In fact, there's a stipulation here. B has to be a positive number, and it has to be greater than 0, positive, but it can't be 1. So like, it could be like y equals 2 raised to the x, or it could be something like y equals 1/3 raised to the x. Any kind of number that's positive and not 1 works. Okay? So let's look at a problem that deals with an exponential function. Example 1 here says the exponential function f of x equals 42.2 times 1.56 raised to the x power models the average amount spent, f of x, at a shopping mall after x hours. So f of x is the amount spent, x is the hours. And the question asks us, what is the average amount spent to the nearest dollar after 4 hours? Okay. So 4 hours means they told us that x equals 4, because x is hours. So plug 4 in for all of the x's. We have f of 4 equals 42.2 times 1.56 raised to the 4th power. And so then I'm going to go to my calculator and see what I get. 42.2 parentheses 1.56 close parentheses, and then I do a caret for my power, and I put 4. And so there's my answer, 249.93. Okay. Now here's the thing though, that would be my exact answer, but they asked us to go to the nearest dollar, so that really goes to $250. So it's pretty easy to do exponential functions in your calculator. Just remember that you need to use a caret when you do your power. Now, exponential functions are a little bit different than linear functions. If you remembered linear functions, if you had a point and they're on a line, if you went over a certain amount, like say you went over 1, you would go up 1 to get to the next point. And then you'd go over 1 again, and you'd go up 1 again to get to the next point. Okay. Or something like that. It's a constant rate of change. It's meaning like it always adds the same amount or it subtracts the same amount from the y value. So like it always goes up by 1 or always goes down by 3 or something like that. Exponential functions, on the other hand, don't do that. So like, as an example, here, this y value might be at 1/2, and then this one's at 1, and this one's at 2. Well, going from 1/2 to 1, that's going up by 1/2. But going from 1 to 2, that's going up by 1. So it's not going up by the same amount each time. Instead, exponential functions are multiplicative, meaning it multiplies by a number instead of adding by a certain number. So like to go from 1/2 to 1, you multiply by 2. To go from 1 to 2, you multiply by 2. And so they're a little bit different than linear functions. Okay? Now with that being said, any exponential function that you do find can be written in this form: f of x equals c times b raised to the x, where b represents that number you're multiplying by every time. So if we look at a table of data, we can actually determine whether or not a function is linear or exponential just by looking at what happens with the points. Is there a constant addition subtraction? Then it's linear. If there is a constant multiplication or division, then it's exponential. If it's neither of those, then it's neither. So let's kind of take that and go with it. So example 2 right here asks us to look at some tables and determine whether the given function is linear, exponential, or neither. If it's linear, we're going to write a function to model that it's linear. And if it's exponential, we'll write an exponential function to model it. Look at your first table. Okay. The x's all go up by 1, so it's going up 1 each time. The y's, going from 5 to 2, going from here to here, that's going up by 3. It's adding 3. Subtracting 3. If you're going from 5 to 2, you are subtracting 3. And then when you go from 2 to negative 1, that is also subtracting 3. Negative 1 to negative 4, that's also subtracting 3. Negative 4 to negative 3, that's also subtracting 3. So since it's an addition or subtraction thing, this function here is linear. And this number that we are subtracting each time, that's our slope. So our slope is negative 3. And so we can pick any point and use our slope, and we can write an equation of the line. So I'm just going to use this first point, and I'll say y minus 5 equals negative 3 times x plus 1. Yeah, I could have used any of the points. I could have used 0, 2, or 1, negative 1, or 2, negative 4, or 3, negative 7, and it would have been okay. But there's my equation for that line. Alright, let's look at B. Again, the x's are still going up by 1. If we look at our y's, to go from 32 to 16, that's going down by 16. To go 16 to 8, that's going down by 8. To go to 8 to 4, that's going down by 4. And to go down from 4 to 2, that's going down by 2. Are they adding or subtracting by the same amount? No. So it's not linear. So let's see what happens if we go with multiplication or division. Going from 32 to 16, that's dividing by 2 or multiplying by 1/2. Going from 16 to 8, that's dividing by 2 or multiplying by 1/2. Going from 8 to 4, that's dividing by 2 or multiplying by 1/2. And going from 4 to 2, that's dividing by 2 or multiplying by 1/2. So it is multiplying by the same number every time. It's multiplying by 1/2. Since it is the same number being multiplied, this function is exponential. And this number that we're multiplying by is our b. Our b is 1/2. Now here's the thing. Exponential functions follow this form up here. F of x equals cb raised to the x. We know b, and x is our variable, but we don't know c yet. So what we have right now is we have f of x equals c times 1/2 raised to the x. Well, I'd like to figure out what c is. To do that, just pick a point off this table. Any point works just fine, and plug in. I'm going to do 1, 8. So I'm going to plug in 1 for x and 8 for y. So 8 equals c times 1/2 to the first power. So 8 equals 1/2 to the first power is just 1/2. And 1/2 times c is 1/2 c. And then I can get rid of the 1/2 by multiplying both sides of the equation by 2. 2 times 8 is 16. 1/2 c times 2 is c. So c is 16. So our final equation ends up being f of x equals 16 times 1/2 raised to the x. Okay. So there's that one. Let's look at our final table of data here. Again, if you look at the x's, they go up by 1 each time, so that's fine. Look at our y's. Going from 2 to 4, that's adding 2. Going from 4 to 7, that's adding 3. 7 to 11, that's adding 4. 11 to 16, that's adding 5. Is it adding the same number every time? No. So it's not linear. Alright, let's check multiplication. Going from 2 to 4, that's multiplying by 2. Going from 4 to 7, that's multiplying by 7/4. Going from 7 to 11, that's multiplying by 11/7. Going from 11 to 16, that's multiplying by 16/11. Is it multiplying by the same number every time? No. So it's also not exponential. So if it's not linear and it's not exponential, then it's neither. And luckily for neither, we don't have to find anything else. This is all we had to find, is that it was neither. Okay? So you can determine whether or not a function is linear, exponential, or neither. The next thing we're going to do is graph an exponential function. We're going to start by graphing f of x equals 2 raised to the x, and the directions ask us to use x values that are on an interval -3 to 3. So I have x, and I have y. My x's are going to be 3 to +3. Now remember, if you have an x, to find the y value, you just take the x and you plug it in. So we'll have 2 raised to the -3 power. If you don't know how to do it, you can just go to your calculator. 2 raised to the -3 power, and you get 0.125. Or, if you want, you can change that to a fraction. Math fraction, that's 1/8. And there's a special reason why it's 1/8. We're going to review exponent rules at the end of this lesson, but when you have a negative exponent, what the negative does is it causes the number to get flipped to the bottom of the fraction. So like 2 to the 3rd power is 8, but then that negative exponent flips it to the bottom, so you end up with 1/8. That's what a negative exponent does. Alright. -2, if we plug in, we have 2 to the -2 power. Again, if you don't trust yourself, go to your calculator. 2 raised to the -2 power. That's 0.25. Yeah, 1/4. And again, it makes sense. 2 squared is 4, and the negative flips it to the bottom, so it's 1/4. Alright, -1, 2 to the -1 power. And if you don't trust yourself, use your calculator. 2 raised to the -1, it's 0.5. And again, it should make sense that it's 0.5, because 2 to the 1st power is 2, the negative flips it to the bottom, so that's why we have 1/2. Alright, 2 to the 0 power. Hopefully you know anything to the 0 power is 1. But if you want to verify, in your calculator, 2 to the 0, that's 1. Alright, 2 to the 1st power. 2 to the 1st power is 2. 2 to the 2nd power, that's 4. And 2 to the 3rd power, that's 8. Now, since we're going all the way up to 8, I do want to make sure that this was high enough. So if this is 8, 7, 6, 5, 4, 3, 2, 1, 0. So this right here is 0. So when I draw my axis lines, this is where I'm going to draw my x-axis, and then I'll draw my y-axis here in the middle. And then I'm just going to plot these points. So I've got -3 and then 1/8, -2 and 1/4, -1 and 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. So we'll just kind of connect those together. And do make sure you put arrows on the ends so you know it keeps going in both directions. Everybody okay there? Now you might notice this arrow, I didn't make it point down, I made it point to the left. That's because as we go down, we will get closer and closer to 0, but we'll never actually touch 0. Like as you make x become more and more negative, those fractions that you get are going to get smaller and smaller. So like you'll have 1/8, and then 1/16, and then 1/32, and then 1/64, 1/128, 1/256, 1/512, 1/1024, etc. Like the fractions are just going to keep getting smaller and smaller, but they're never going to get to 0. They're just going to get so small that they might as well be 0, but they will not actually be 0. Okay? So where it's not going to continue down, it's just going to keep going to the left. Let's do another one. Example 4, we have g of x equals 1/2 raised to the x. We're asked to use x values going from -3 to 3. Again, I'm going to make myself a table, x and y. X's go from -3 to +3. And then if I have x's to find y's, I just plug in. So I'm going to have 1/2 raised to the -3. I can already tell you this is 8. You can verify it in your calculator. If you do 1/2, and then you raise it to the -3 power, you get 8. And the reason why is the negative flips that fraction. So instead of being 1/2, it becomes 2. And 2 to the 3rd power is 8. Okay. When you plug in -2, you have 1/2 to the -2 power. It's going to be 4. The negative is going to flip the fraction, so it becomes 2. 2 squared is 4. 1/2 to the -1 power. The negative flips it, so you get 2. 2 to the 1st power is 2. Plug in 0. 1/2 raised to the 0 power is 1. Because anything raised to the 0 power is 1. Plug in 1. 1/2 raised to the 1st power. 1/2 to the 1st power is just 1/2. 1/2 raised to the 2nd power. The 2nd power goes to the 1 and to the 2, so 1 squared is 1. 2 squared is 4, so it's 1/4. And then 1/2 to the 3rd power. 1 squared is 1. Sorry, 1 cubed is 1. 2 cubed is 8. That's 1/8. And once again, we're going to go all the way up to a high y value of 8, so I want to make sure I start up here as this is 8. So 8, 7, 6, 5, 4, 3, 2, 1, 0. So 0 right here. So we'll draw our axis lines. And then we'll plot our points. So at -3, we're going to be up here at 8. At -2, we'll be at 4. At -1, we'll be at 2. At 0, we'll be at 1. At 1, we'll be at 1/2. 2, we'll be at 1/4. And 3, we will be at 1/8. Sorry, I'm going to redraw that. Didn't come out quite right. So there's our graph, and again, it continues to the right. It's never going to get to 0, and it'll just kind of approach 0. So here are some characteristics of exponential functions in general. All exponential functions are going to have a domain -infinity to infinity. That's always true. Even if you transform an exponential function, it will still have that domain. The range of an exponential function is 0 to infinity. As I said, it will never get to 0, but it'll get really close. So we don't include the 0. It's 0 not included to infinity. Now, if we perform transformations on an exponential function, then that range might change. Like if we shifted the graph up 4, then instead of going 0 to infinity, it's going to go 4 to infinity. So it just kind of depends. The second characteristic is all exponential functions are going to go through the point 0, 1, and 1b. And that's just because b raised to the 0 power Like anything, no matter what b is, b to the 0 power is always 1. And then for 1 comma b, b to the first power is always b. Like if you take a number and raise it to the first power, you're always just going to get that number, no matter what. Okay. So here's a couple other things. If your number here is bigger than 1, like 2, 3, 4, 5, 6, 7, whatever, then your graph is going to look like this. It's going to be like what we just did in example 3 there. Okay? It's going to be going up to the right, and it's going to be increasing. If, on the other hand, your b is between 0 and 1, your graph is going to look like this, just like we did in example 4. It's a graph that goes down to the right, and it is decreasing. So just by looking at the base number on the exponential function, you can determine whether or not it's going to be an increasing exponential function or a decreasing exponential function. Number 5, these functions are one-to-one. And since they are one-to-one, we learned back in 6.2 that means they have inverse functions. And so later on in Chapter 6, we will talk about the inverse function for an exponential. We're not there yet, but we will get there. Okay. And then the last thing is the graph approaches but does not touch the x-axis. And the real reason behind that is there is a horizontal asymptote there at y equals 0. Now again, if your graph is transformed, if it gets shifted up or down, then that asymptote would move, and it wouldn't be y equals 0 anymore. Now, speaking of transformations, that's what we're going to do next. Transformations of exponential functions pretty much work the same way as they did in earlier chapters. You first have to identify the parent function. So, like, is your parent function 2 to the x, or is it 3 to the x, or is it 5 to the x, or 6 to the x? Like, what is the parent function? And then, once you've identified what the parent function is, then you apply transformations to it. Now, for exponentials, things that are in the exponent affect the x, but just like usual, they affect the x in an opposite operation. So, like, if it says 2 raised to the x minus 4 power, the x minus 4 there affects the x, but it does it as an opposite operation. So you're really going to do x plus 4. Okay. Now, the things that are not in the exponent affect the y. So, like, if you have 2 to the x power plus 7, that plus 7 is not in the power, and so it does not affect the x, it affects the y. And so you're going to add 7 to the y's. Alright, so let's do a couple examples of transformations. So example 5 here says, use the graph of f of x equals 3 raised to the x power and the points on it to obtain a graph of g of x equals 3 raised to the x plus 1 power. So they're saying, hey, we've got this transformed function. Here's its parent function, 3 to the x. Use the points on it to get a graph of this. And they were even really nice. They actually gave us a table of the points. So for 3 raised to the x, when x is negative 2, the y is 1/9. When x is negative 1, the y is 1/3, etc., etc. Okay? So this is my table of values for the original function. But we have a transformation here. There's a plus 1 up here in the exponent. Now, since that plus 1 is up in the exponent, it affects the x. But it does it in an opposite operation. So what we're going to do is we're going to do x minus 1. But we'll leave the y values alone. We won't do anything to those. So we'll still have a y value of 1/9, 1/3, 1, 3, and 9. All we got to do is change the x's. And so on the x's, we're going to subtract 1. So negative 2 minus 1 is negative 3. Negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. 1 minus 1 is 0. And 2 minus 1 is 1. And then we want to draw our graph. Now, this is going up to a y value of 9, so let's see. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So 0 is going to be down here at that lower line. So there is my x-axis. There is my y-axis. And then I'm just going to plot these points. 1, 2, 3, and 1/9. Negative 2 and 1/3. Negative 1, 1. 0, 3, and 1/9. And so there's my graph. And so by having that +1 up there in the exponent, we've shifted our graph horizontally to the left 1 unit. All of the points are 1 unit over to the left. Okay. Get another one. It says use the graph of f of x equals 2 raised to the x power and the points on it to obtain the graph of g of x equals 2 raised to the x power minus 3. So again, we have a transform function here. They've given us the parent function. The parent function is 2 raised to the x. And once again, they were really nice and gave us a table of points for it. So we didn't have to make it ourselves. Now in this function, we have a transformation, a minus 3. This minus 3 is not in the exponent. Since it's not in the exponent, it affects the y. So in this case, our x's are going to stay the same, but for our y's, we are going to take away 3. So our x's are still going to be negative 2, negative 1, 0, 1, and 2. For our y's, though, we're going to take away 3. So if I take 1/4 and I subtract 3, I get negative 2.75. If I take 1/2 and I take away 3, I get negative 2.5. And then for whole numbers, it's pretty easy. 1 minus 3 is negative 2. 2 minus 3 is negative 1. 4 minus 3 is positive 1. And so then we need to plot those points. Since this is almost negative 3, I'm going to say, let's make this negative 3. So that's negative 2, negative 1, and that means this is 0 right here. So there's my x-axis, my y-axis, and I'm just going to plot these points. So at negative 2, we are down at negative 2.75. At negative 1, we're down at negative 2.5. At 0, we're at negative 2. At 1, we're at negative 1. And at 2, we are at positive 1. Alright, so there is a function. So it's the same as this function, except we just shifted it down 3 units. Okay? Now that does mean that the horizontal asymptote changed. Originally the horizontal asymptote was at 0, but now because we've shifted it down 3 units, the horizontal asymptote is going to be down here at negative 3. Now one thing I want to point out right now before we move on to the next little bit is that when you do these in my math, a lot of times they use their little transformation toolbars, where rather than plotting points, you just say, hey, there's a vertical shift of whatever, there's a horizontal shift of whatever, and you just use little toolbars or whatever, the sliders, to make it work. With these, though, you have to be careful, because there's a little box you have to fill in. It says, what is the base? Well, the base is the number that has the exponent on it. So, like, in this problem, the base would be 2. And so you have to make sure you change that appropriately, otherwise it'll mark your graph wrong because it'll draw the graph in the wrong base number. So make sure you change the base number when you're using the MyMathLab graphing utility. All right, now we have a special base number that we're going to talk about next, which is the number e. Okay. The number e is called the natural base. It comes up a bunch in nature, which is why it gets the name natural base. Okay. Now, e is an irrational number. It's not just a letter, it's a number. And it's an irrational number. Remember, irrational numbers are numbers like pi. They have decimals that go on forever without end. They do not repeat. They just keep going on with different patterns, and then they just repeat forever. Don't repeat, and they just keep going forever. Okay. Yeah, e is kind of that way. Okay. E is a number. It's approximately 2.718281827. There's even more decimals. After that, I just stopped after this point. Most calculators have E on them. On the TI-84, the E is found right here in blue above the LN button. So to use it, I hit second, and then I hit the LN button, and that'll put in E with a little caret. And if I want to find out what E to the first power is, there it is, 2.718281828. Okay? And it's not showing all of the digits, but it does have them in there in the calculator. So that's E. Now, where does E come from? It actually comes from this formula here, 1 plus 1 over n, all raised to the n power, and we make n approach infinity. As n approaches infinity, as it gets closer to infinity, this formula, this expression, is going to get closer and closer to this number E. Now, if you want a proof of that, you might want to take Calculus 2, because in Calculus 2, you can learn about things like L'Hopital's rule for solving problems like this, n goes to infinity, and you can prove that this is actually E. Okay. Now, as I mentioned earlier, E is called the natural base. It comes up a bunch of times in nature. And so when we write an exponential function with a base of E, it's called the natural exponential function. So the natural exponential function is f of x equals e to the x. Now, you can graph it and do things with it just like you do any other exponential function. You'll just have to use your calculator to help you find the values, because you're not going to do e squared in your head. You're going to have to use the calculator to find e squared. The last thing we're going to look at today is exponential equations. Now, exponential equations are equations that have exponentials in them. So something like 3 raised to the x power equals 9 is an exponential equation. Now, I'll even write down what I just said, because sometimes I know it's hard to visualize. So what I would just said was 3 raised to the x power equals 9 is an exponential equation. Okay? It's an equation, it has an equals sign in it, and it's exponential because it has an exponential function in it. Now, there are several different ways you can solve exponential equations, but the way that we're going to look at today is by getting a common base. What I mean by that is 3 and 9 here are both powers of 3. 3 is already a power of 3, so I can leave it alone. But 9 could be rewritten as a power of 3. 9 is 3 squared. Now, once we have this statement, 3 raised to the x equals 3 squared, if this is mathematically true, we know that x up here has to be equal to 2, because that's the only way these two things can be equal. If x is 5, 3 to the 5th does not equal 3 to the 2nd, so it doesn't work. So basically, if you can get them to the same base, then you can just set the exponents equal to each other, and you can actually figure out what your answer is. And that's what the little property down here says. You can kind of see it. It says if b raised to the u power equals b raised to the v power, then u has to equal v. So if you have the same base number, then your exponents have to be equal to each other. Now here's where we need to review our exponent rules, our laws of exponents. Because many times, in order to get a common base, you're going to have to use exponent laws to simplify expressions. And so I want to quickly just review a couple of the exponent laws, make sure everybody's okay with them. So the first one says if you have a raised to the s power times a raised to the t power, it equals a raised to the s plus t power. So when you have multiplication between two things that have the same base, you add the exponents together, s plus t. There's a kind of another version of this that looks kind of like this. A to the s divided by a to the t equals a to the s minus t. Okay. Works the same way. It says if you have division of two things with the same base, you subtract the exponents. So you have a raised to the s minus t power. Our next property, when you have a to the s raised to the t, it gives you a to the st power. So what that means is when you have a power getting raised to a power, you multiply the powers. Okay. Our next one, ab raised to the s power is a to the s power times b to the s power. So when you have multiplication or division and you have an exponent, the exponent goes to all of the stuff inside. Now I want to caution you here, a plus b to the s does not equal a to the s plus b to the s. It doesn't work that way. You cannot distribute into addition or subtraction like that with exponents. Just to prove it to you, if I had 2 plus 5 raised to the second power, that does not equal 2 squared plus 5 squared. I can prove it. What's 2 plus 5? 2 plus 5 is 7. 7 squared is 49. Over here, 2 squared is 4. 5 squared is 25. 4 plus 25 is 29. 49 does not equal 29. Okay? So it doesn't work. You can only make the exponent go in if it's multiplication or division. Okay. Our next exponent power, 1 raised to any power equals 1. That's always true. Our next one after that, a raised to the negative s power is the same thing as 1 over a to the s power, which is the same thing as 1 over a all raised to the s power. Okay. So the negative just causes things to flip to the bottom of a fraction. Or you can read it the other way. If it's on the bottom of the fraction, you can flip it back up and make it a negative exponent. Right. Our last rule, a raised to the 0 power equals 1. Anything raised to the 0 power is always going to equal 1. Okay. So let's go solve some exponential equations. Example 7 asks us to solve these exponential equations. Part A we have, if you write it over here, 3 raised to the x plus 1 equals 81. The first thing I want to do is I want to get a common base. Is there a common base for 3 and 81? Yeah, there is. The base is 3. 3 is already base 3, so this is 3 raised to the x plus 1. 81 is 3 raised to the 4th power. And you can check it in your calculator. 3 raised to the 4th, that's 81. Now that these two things have the same base, we set the exponents equal to each other. So we say x plus 1 equals 4. And then we solve for x, so subtract the 1, x equals 3. Alright, let's look at B. B, we have 4 raised to the 2x minus 1 equals 8 raised to the x plus 3. is there a common base for 4 and 8? Are 4 and 8 both powers of something? And they are. They're both powers of 2. 4 is 2 squared, and then that 4 is getting raised to the 2x minus 1 power. 8 is 2 to the 3rd power, and then that 8 is getting raised to the x plus 3. Now here's where we need to use our exponent rules. On the left-hand side here, I have a power getting raised to a power. When you have powers raised to powers, you multiply the powers. So I'm going to end up with 2 raised to the 2 times 2x, which is 4x, and 2 times negative 1, which is negative 2. On the right-hand side, I have a power getting raised to a power, so I multiply the powers. So I'm going to have 2 raised to the 3 times x, which is 3x, and then 3 times 3, which is 9. At that point, they now have the same base, so we can set the exponents equal to each other. So 4x minus 2 equals 3x plus 9. Subtract the 3x over, so we have x minus 2 equals 9. Add the 2 over, we get x equals 11. So there is our answer. Alright, number 8 asks us to solve the equation e raised to the negative x squared power equals e to the x raised to the 2nd power times 1 over e to the 3rd power. So the first question we asked is there a common base for e, and e? And the answer is yes, the common base is e, which they already have. All we really have to do is simplify this using our exponent rules. Now, there's nothing I can do on this left-hand side. I just have to kind of leave it as e to the negative x squared power. On the right-hand side, here I have e to the x getting raised to the 2nd power. So I have a power getting raised to a power. When a power gets raised to a power, we multiply the powers. So we'll have e to the 2x power times. Here, I have 1 over e to the 3rd. E to the 3rd is on the bottom. Well, according to my exponent rules, if it's on the bottom, originally it was a negative exponent. It was e to the negative 3 power, because the negative caused it to flip down to the bottom. Now we're not quite done simplifying. We can do a little bit more. Here on the right-hand side, I have 2 things getting multiplied together. When you multiply them together, you add your exponents. So we'll have e raised to the 2x minus 3 power. Now, you could write 2x plus a negative 3, but it makes more sense to write 2x minus 3. At this point, they now have the same base on each side, and so we can set our exponents equal to each other. Negative x squared has to equal 2x minus 3. Now, because there are x squareds and x's in this problem, I would like to set my equation equal to 0 so that I can either use the quadratic formula or factor. So I'm going to take this negative x squared, and I'm going to add it over to the right-hand side. So I'll have 0 equals x squared plus 2x minus 3. And then at that point, we can either factor or use the quadratic formula. I'm just going to factor it. To make x squared, I need x times x. In order to make a 3, I would need 1 times 3. And in order for it to be a positive 2 in the middle, the 1 would have to be a negative and the 3 would have to be a positive. Once it's factored, then we can set the factors equal to 0, and we can solve. And so we get x equals 1, and we get x equals negative 3. Okay. one last example, and then we are done for today. So our last one is a word problem. It says, between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 12 cars per hour, which is 0.2 cars per minute. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 p.m. So t here measures minutes, and the formula gives us a probability. So f of t equals 1 minus e raised to the negative 0.2 t power. I want to talk about probability real quick before we get into the problem. Okay. Probability, which I'm just going to use p for, is a number that's always between 0 and 1. Okay. 0 means that whatever you're talking about is impossible. There is no way it can happen. It is literally impossible. Okay. 1, on the other hand, means it is certain. It is going to happen. There is no way it doesn't happen. It has to happen. Okay. Any number in between those two is some variation. So, like, if p ends up being 0.5, that's like saying there's a 50% chance it's going to happen. If p equals 0.25, then that says like there's a 25% chance it'll happen. Okay. So p just kind of gives you a number that tells you what is your likelihood that an event will occur. Okay. All right, so let's get into our problem. Part A asks us to determine the probability that a car will arrive within 5 minutes of 9 p.m. Well, 5 minutes, t is minutes, so we're going to plug 5 in for t. So we have f of 5 equals 1 minus e raised to the negative 0.2 times 5. And then I'll go to my calculator. 1 minus, to do my e, I'm going to do second ln. And inside this e, I'm going to have negative 0.2 times 5. And so there we go. I'm going to round it to 3 decimals, so this is 0.632, or a 63.2% probability. So that means it's about a 63.2% chance that a car is going to arrive within 5 minutes of 9 p.m. All right. Part B. Part B asks us to determine the probability that a car will arrive within 30 minutes of 9 p.m. So they've given us 30 minutes. T is minutes, so we'll plug 30 in for t. So we'll have f of 30 equals 1 minus e raised to the negative 0.2 times 30. And then we'll go to our calculator. 1 minus e raised to the negative 0.2 times 30. So if I round that to 3 decimals, that's 0.998, or a 99.8% chance. Okay, now notice it's not a 100% chance. It's not saying for certain that somebody is going to pull up at the Burger King drive-thru within the first 30 minutes. It's just saying that there's a 99.8% chance that at least one car will pull up during that 30-minute time period. All right. Part C asks us to graph this function using a graphing utility. So I'm going to use my graphing calculator. I'm going to go into y equals. I'm going to clear out this stuff that's already in there. And so I'm going to put in this equation. Now, when we put it in, we can't put in t. So we're going to have to use x instead for t. So I'm going to have 1 minus e raised to the negative 0.2 times x. Now before I hit the button to graph, I'm going to go change the window, because I want it to kind of fit here. So x represents time since 9 p.m. Well, the least amount of time we can have is 0. The most amount of time, it just kind of depends. It tells us that this is between 9 p.m. and 10 p.m., so that's about a 60-minute period. So I might make my x max go to 60. All right. Y in this problem represents our f of t. And remember, f of t is a probability. And probabilities go from 0 to 1. So my y minimum is 0, my y maximum is going to be 1. And so when I graph it, there's my function. And I can actually use the trace feature, and I can trace along and look at certain values and kind of see what happens. But this is kind of what happens. It looks like it's going to get closer and closer to 1 and not approach it. In fact, I might make my y max go a little bit higher just so I can see the graph a little bit better. So you can see it kind of gets closer to 1 and then it kind of flattens out because it can never get to 1. It can never be a 100% chance that's going to happen. But it'll get ridiculously close. So I'm just going to draw a quick little sketch of this. So at time 0, it has a 0% chance, and then it kind of goes like this and flattens out, where this is 1. Okay. And so here, the x-axis is time in minutes, and the y-axis is the probability. Okay. And then part D asks us to identify what value the function approaches as t increases without bound. Okay, well, we kind of already talked about this, but if you use trace and you make the x keep getting bigger, what is the y value getting closer to? Well, if you look, it's getting closer and closer to 1. I don't know what happened to my calculator there. But if you keep going, it just gets closer and closer. Like you can see, it keeps adding more 9s to this number. So I can write down 0.9999999, and I'm at 58 minutes right now. If I go to 60 minutes, look how, like, that's so close to 1. And I can keep going. I can keep going until my calculator can't go anymore. Alright. So you can keep going until your calculator really can't hold any more decimals. Like, my calculator's going to start having problems in just a second. It has to keep adding digits on because it can't hold any more numbers. And see, now it can't even show the difference anymore because it's, look how close it is. At 92 minutes, it's basically 1. So as time goes towards infinity, as time increases, that f of t, that probability, is getting closer and closer to 1. It's never going to get to 1. It's never going to be a 100% chance that it happens. But it's always going to increase towards 1. It'll keep going towards 1. Okay. So that is the end of our notes for today. Let me know if you have any questions.